fundamental problem 22 from chapter 16. At the instant shown, cable AB has a velocity of 3 meters per second and acceleration of 1.5 meters per second squared, while the gear rack has a velocity of 1.5 meters per second and acceleration of 0.75 meters per second squared. Determine the angular acceleration of the gear at this instant. So we have equation 1618 to use. In the book for equation 1618, they do it with points A and B. Well, we have the acceleration of the rope here and the gear rack. So we're going to use point A, and I'm going to call this point here where the gear is touching the gear rack point C. So they kind of indicate here that the whole gear rack is point C, but I'm going to call, or the whole gear rack is C, but I'm going to call this point here point C and make it a point on the gear. Okay, so I have point C and point A, so I'm going to use equation 1618 with point C and point A rather than point A and point B. Now I can do this either way. I can either make the B in this equation is C, and that gives me this here, or I can flip the A's and the C's around. If I flip the A's and the C's around to get back to the equation that I have here, I would bring the AC over to this side and the AA over to this side, which would change the signs. However, for the position vector here, the signs would be opposite as well, because here you're going from point C from point A, and in this equation, this should be to point A from point C. So the equations are the same, except for the signs would change in each term. So you can do it either way. I'm asked to find the angular acceleration here. Now, I know the angular acceleration is either in the positive k-hat direction or the negative k-hat direction. I'm not going to make an assumption about whether it's in the positive k-hat direction or the negative k-hat direction. I'm going to solve for it and let the sign tell me what direction it's in. So let's use this equation here, okay? You can try it using the other equation, this one, on your own, and check to see that it works out. So I'm just going to focus on the cross product here. So the angular acceleration crossed with the position of A with respect to C, and see what that gets me. So the angular acceleration, which could be this, could be positive or negative, in the k-hat direction, crossed with the position of A with respect to C. So that's pointing to point A from point C. If I go back to the book, if I say this is point C, I'm going all the way to point A. The inner radius is 0.2, the outer radius is 0.3, so that's 0.3 from here to here and 0.2 from here to here. So the whole distance is 0.5 meters. And since we're going to point A from point C, that's in the positive j-hat direction. Now I'm going to do this cross product here. K-hat crossed with j-hat is negative I-hat. So that's in the negative I-hat direction. I have my 0.5 meters. And I have my angular acceleration. So this is what I have for the cross product. This is in the I-hat direction. Now, if I look at everything that I have here, I don't have the angular speed, but the direction of the angular speed does not matter. It's just the direction of this position vector here. Actually, I should be looking at this equation here. This position vector is pointing in the j-hat direction. This here only has an I-hat component. I'm only asked to find the angular acceleration. So if I can just look in the I-hat direction and find the angular acceleration just by looking in the I-hat direction, then I can ignore this. I have the acceleration of A and the acceleration of C. Now I have to be careful here, because if they give me the acceleration of the rope here if this point A is a point on the gear, not only does it have tangential acceleration pointing this way, it also has a component pointing in towards the center of the wheel. So if this is a point on the wheel, remember that anytime you have a point which is moving in a circle, as long as the velocity is not zero, if it's going in a circle, you have acceleration pointed in towards the center of the circle. Similarly with point C, if this is a point on the wheel, it must have a component of acceleration pointing in towards the center of the wheel, in addition to a component which is pointing this way. Now, if I only look at the I hat components, then I'm in luck, because this component and this component are pointing in the negative j hat direction and the positive j hat direction. So if I can find what I'm looking for without looking in the j hat direction, it will be a lot easier. Okay, so we're just going to look at the I hat terms rather than writing out the whole equation. I already did the cross product. I know that for the cross product, I just have an I hat component. So writing down only the I hat terms, acceleration of point A, that is the same as the acceleration of the rope in the I hat direction. So this is 1.5 meters per second squared I hat is equal to, for the acceleration of point C, that's in the negative I hat direction, that's 0.75 meters per second squared. So this is minus 0.75 meters per second squared I hat, plus the cross product which I have here, which I already figured out, was negative 0.5 meters times the acceleration, angular acceleration in the I hat direction, and then this term only has a j hat component. Now, if you were to look in the j hat direction, you would have a component of this acceleration in the j hat direction, a component of this acceleration in the j hat direction. This has no j hat component, and you can figure out what this is. Now, they only asked us to find the angular acceleration, so I don't have to look at the j hat components. If I was looking for the j hat component of this acceleration or the j hat component of this acceleration, I may have to look at the j hat components, or maybe I could go back to my equation for the normal and tangential components, and the component which is pointing in towards the center of the circle is the normal component, and that's equal to negative omega squared times the vector r. So you could also use that to find the normal components if you find the angular velocity, or yes, the angular velocity here. Okay, so we're kind of taking a shortcut to solve this problem by just looking in the I hat direction, because that's all I need to do here in order to find the angular acceleration. Now I can take this and solve for the angular acceleration. I have to bring the 0.75 over to the other side. So I have 1.5 meters per second squared plus 0.75 meters per second squared divided by negative 0.5 meters gives me the angular acceleration. And that is minus 4.5 radians per second squared. The minus sign tells me, because I just called the angular acceleration alpha times k hat, that it's going in the negative k hat direction. So this is minus 4.5 radians per second squared in the k hat direction, which is all that I was asked to do. Now, if I didn't realize ahead of time that I only have to be concerned with the I hat components, then I would have been looking at this term here. We can find the angular speed in this case, so let's do it just for fun. Okay, so if we were following our usual procedure to solve this problem, we would first be looking for what to put in to this equation for the different quantities that we have. So for fun, we're going to find the angular speed. I can do this using the instantaneous center of zero velocity. Okay, I'm going to redraw what I have up here, sort of, down here. This is point A. The speed of point A is 3 meters per second this way. Down here I have point C with a speed, point C is there, with a speed of 1.5 meters per second going the other way. Now, well, I should have drawn the vectors to scale. So 1.5, that's half of 3, so let's make this a little smaller. Okay, now I can draw a line between point A and point C and draw another line connecting the tips of the two arrows, and this shows me the location of the instantaneous center of zero velocity. Now I know for the instantaneous center of zero velocity, I can say the speed of point A, which is 3, is equal to the angular velocity of the gear times the position of A with respect to the instantaneous center. Can do the same thing here and say the speed of point C, which is 1.5, is equal to the same angular velocity times the position of C with respect to the instantaneous center. I don't know what this distance is from point C to the instantaneous center, but I know if I go all the way from point A to point C, which we did up here to get this vector, that whole distance is 0.5. That's the inner radius times the outer radius. So I can say, well, here we're just doing it with a scalar equation, so it's just the distance here. If I add this distance plus this distance, so that would be to point A from the instantaneous center plus the distance to point C from the instantaneous center, that must add up to 0.5. So if you take these three equations and put them together, you can find the angular speed. So let's take this equation and this equation and solve both of them for omega. So we have omega is equal to 3 divided by the distance 2a from the instantaneous center. From this equation we have 1.5 divided by the distance to point C from the instantaneous center. Then let's take our equation here and solve it for the distance to point C from the instantaneous center. That is 0.5 minus the position of A from the instantaneous center. So take this and put it in here. And then we'll take this whole thing and bring it down here. We have 3 divided by RA over IC is equal to 1.5, and this is 0.5 minus RA over IC. Let's divide by 1.5 on both sides, so 3 divided by 1.5 gives me 2 on this side. Then multiply both sides by RAIC and also multiply both sides by 0.5 minus RA over IC. And distribute the 2 here, so that's 1 minus 2 times RA over IC is equal to RA over IC. If you bring this over to the other side, you have 1 is equal to 3 times RA over IC. So RA over IC is equal to 1/3. The units for that should be meters, so it's 1/3 of a meter. You can take that, so let's say 0.333 meters. You can take this, put it back up here, and you get omega. If you bring the RAIC over to the other side, you're dividing by 1/3, which gives you 9. And this is radians per second squared. Okay, which we did just for fun, but if you found this, you could go back to your equation here, put in the 9 for omega, then you need this vector, which we found here is 0.5 in the j-hat direction, but since it's only pointing in the j-hat direction, it doesn't appear when you look at the I-hat components. Okay, and then looking at the j-hat components, you have the unknown component for this acceleration and the unknown component for this acceleration also, which we were not interested in finding. And so all of this didn't really help us find the solution. But anyways, it was fun finding it. Okay, so that concludes fundamental problem 16-22. So when you're using this equation here, it's helpful to ask yourself how many unknowns you have. And let's say I was looking for the acceleration of point C or the acceleration of point A. Actually, let's go back and look at what we saw in the previous problems. Okay, so for fundamental problem 19, I was looking for the acceleration of B and the angular acceleration. So that's 2 unknowns. So if I go back here, I needed to say what the acceleration of A was. So I have magnitude and direction here. And because I have 2 unknowns, that means I have to be able to say what the angular speed is and what this position is. So I had to find this angular speed so I could find my 2 unknowns in this problem. Fortunately, in this problem, just by looking at it, I'm able to say that this acceleration only has a j-hat component. Okay, then in problem 21, because the acceleration here that I'm looking for has a non-zero I-hat component and a non-zero j-hat component, I have to be able to say what this acceleration is. And I also have to find the angular acceleration. In addition to that, because I'm solving for an I-hat component and a j-hat component, I had to find the angular acceleration here and put it in, because I have for this an unknown I-hat component and an unknown j-hat component. So looking at the I-hat terms here and the j-hat terms just allow me to find, this was supposed to be a j-hat, just allow me to find those 2 different components. Okay, so here we could use our equation to find 2 unknowns because this only had an I-hat component. This had an unknown I-hat and an unknown j-hat, so we had to be able to say what everything else was. In this problem, 22, we only had one thing we were asked to find. We know what direction it's going in, and so if we just look at the I-hat terms, we can ignore what's going on in the j-hat direction, and so as long as we just look in the I-hat direction here, we can find what we are looking for. Okay, so that concludes fundamental problem 16-22.